Right, so we're back, part 2 of the momentum lesson. A little bit more now, continuing on about the conservation of momentum. You need to know this, that this is a free mark on the exam when they ask you to write down the principle of conservation of momentum. When two or more objects interact, the total momentum remains constant, provided no outside forces interfere. Basically, the total momentum before is the total momentum after, right? And we look at some simple examples. We look at some more now. The diagram below shows two railway wagons, A and B, which are about to collide. They're both going left to right. After the collision, the couplings connect so that the wagons stay joined to each other, i.e. they coalesce, and we now have one mass, right? So effectively, can you now work out the velocity of the new coalesced wagons together? So work out the total momentum before. You know that that will equal the total momentum after. You know the maths, so you can calculate the velocity. So please press pause now and spend 60 seconds calculating that velocity. Okay, thanks. So that was a pretty simple one. The total momentum before, mass times velocity there, mass times velocity there. Add them up, they're going in the same direction. And that gives 14,800. And that's what the total momentum after must equal. They coalesce, so we now have a combined mass of 3,600. Divide those to get the velocity, and it's 4.1 meters per second. So the one has slowed down a bit, and the one has sped up a bit. Okay, no props. Now have a go at this one, please. This time they are colliding head on. So let's call this 5 meters per second as positive velocity and this 3 meters per second as negative. So to work out your total momentum before, you'll multiply these, and subtract them. Again, they coalesce, so you'll have a new combined mass, and then you can work out the final velocity. Okay, which way does it go? So don't forget, we've taken positive as left to right. If it comes out negative, it'll be right to left. Looking at the diagram though, it looks like it's going to stay left to right because this is the heavier mass and it's going faster. So press pause and have a go at that, please. Thank you. Here's the answers to this then. Total momentum before. Again, note the negative sign there, and I get a total momentum of 5,200. And that must equal the total momentum after the collision. I have a new mass of 3,600 because they coalesce. Divide those to get the velocity, and it's 1.44. So they both slow down significantly, but continue in a left to right motion. Okay, no props. Another question they like to chuck on an exam can be used in a gun or a cannonball type of question, where both objects are stationary and we have what's called a recoil after the explosion. Right, so let's look at this one. The diagram shows a cannon of mass 400 kilograms firing a cannonball of mass 2 kilograms with a speed of 100 meters per second. So before, there is no momentum, everything is stationary. And then after, the 2 kilogram cannonball flies left to right at 100 meters per second. So there must be a recoil of the cannon moving slightly right to left to counteract that, to give a total momentum of 0. Okay, so if you look at the numbers here, there's my momentum of the cannonball, there's my mass of the cannon. The minus is reflecting the fact that it's moving right to left as a recoil, and the answer comes out as 0.5 meters per second. Okay, let's look at another one. This time we have a gun. Got a bullet of mass 10 grams fired 400 meters per second from a rifle of mass 3.5 kilograms. So first of all, we've got to make sure you get your units right. What is the recoil velocity of the rifle? So before the rifle is fired, there's no momentum, as they're both stationary. And if we take left to right as positive, then we do the same thing. Okay, the total momentum before is 0. The total momentum after is the recoil momentum of the rifle, which will be negative, and the momentum of the bullet. Chuck the numbers in the calculator, and it comes out as 1.44 1.14 meters per second. Double check that yourself on the calculator for me, please. Okay, nearly there. The last thing before you get stuck into your work, elastic and inelastic collisions. We talk about this in several aspects of physics, but in momentum, just like in energy, if something is elastic, then no energy is lost. Okay, now the only real example you can have of an elastic collision in physics is the collisions between the molecules in a gas. That is an elastic collision. Every other collision will be inelastic because energy will be lost, usually due to heat or sound or light, but mainly heat. Okay, so the example here, crash barriers and crumple zones in cars are specifically designed to absorb the kinetic energy during a crash. So they take out a lot of that energy through the heat and sound of the metal crumpling. Okay, but if a collision is elastic, then there is no loss in energy. So the kinetic energy before will equal the kinetic energy after. So here's your last thing for me now, right? There are 1, 2, 3, 4, 5 questions here. They're all like the ones we've just looked at. You'll have bodies colliding, either head-on or coalescing, and you'll have to work out the final velocities. Do them as we've done the examples. Just draw little circles for your bodies, arrows indicating direction of travel, etc. Where the question asks for, is it an elastic or inelastic collision? Get your initial kinetic energy. Don't forget that's a half mv squared. And then equate that to the final kinetic energy with your new velocity, a half mv squared. And if they are the same, it's an elastic collision, and if they are not, it is inelastic. Okay. So give yourselves a good 15 to 20 minutes to have a go through those 5 questions. Press pause now, and I'll go through them as soon as you press play again. Thank you. So here's the solutions. Number 1, quite easy, just like the ones we did in the example. Here's my 2 bodies. One was stationary, one was moving at 25. Total momentum before was this. And then the total momentum after must equal that. So I knew that 750V had to equal 10,000. So 10,000 divided by that is 13.3 recurring meters per second. Second one, head-on collision. So don't forget you have to use your minus there to indicate this is traveling in the opposite direction. So that's my total momentum before, mass times velocity, and subtract them. After the collision, they both travel left to right, hence the plus there. And you needed the new velocity of the 1300 kilogram body. So equate the momentums, and you get the new velocity is 5.38 meters per second. Then they wanted to find out, was the collision elastic? So the total kinetic energy before, half mv squared. Okay, so there's a half mv squared for the 1300. There's a half mv squared for the other body. Don't forget, when you square them, the negative becomes a positive, so we add them together. The total momentum after, do the same thing on these numbers here. They do not equate in any way, therefore the collision is not elastic, which of course you would expect it because it would have lost energy due to heat and sound. Question 16, bit of a scribble, do apologise. Here's my 2 bodies. You have to work out the mass of the initial one, so don't forget momentum is conserved. So I just do the momentum of that one there and then divide it by the mass of this one. Sorry, the velocity of this one to get the mass. Came out to 770. And then combine that with the second part of the question, and looking at my scribble, I've come out with a new velocity of 2.9. You might want to double check that. Do the same thing to work out if it's elastic or inelastic. Work out the half mv squareds before, work out the half mv squareds after. They are different, look. so it's not elastic. Question 17 and 18, top half here is 17, so a head-on collision. Getting the hang of it hopefully now. Don't forget the minus there because the 5 is traveling right to left. Get your total momentum, equate that to the total momentum on the right, so divide through by the mass to get the velocity of 0.4. And then a similar one, question 18 to finish, the ice skaters, they're both traveling in a west direction, right to left. Get the total momentum before they coalesce, which means find the total of their masses, and you can work out the new velocity, and it was 3.6 meters per second to the west, right? So obviously when I see you next in class, I'll answer any questions you have on this, and then we'll look at the official homework on it and do some more work on kinetic energy. Thank you for sticking through the vids. Okay, give us an email if you have any questions. Right, nice one kids, goodbye.